Hello everyone, welcome to the soft computing lecture series. We are doing fuzzy logic. In the last lecture we saw the classical sets and the properties of classical sets. Today we will be doing the fuzzy sets and the properties of fuzzy sets. So what in case of classical sets, as we saw, the change in the membership and the non-membership value of an element is abrupt. Okay? It suddenly changes from like it is a member to it is not a member. Like suppose if we have a graph, okay, suppose if we draw a graph, suppose we have this graph, suppose, and let us assume we have this is the membership value, okay, and this is suppose gives the age. So we define a crisp set which defines the young, okay. So let us assume we define this as 30. So this is suppose 30, okay. So anyone which is who is coming from the 0 to 30 is will be classified as young, and above 30 all are not young. So this is how we the things change from they are the member of this particular set, or they are not the member. So here we can see there is an abrupt change when we cross this 30. But in case of fuzzy logic, what happens is that this change is not abrupt, okay. This change is not abrupt. We may have like a in that case, suppose if we define another fuzzy set, if we define some fuzzy set, in that case, okay, it may happen that we have like a graph of this type, okay, a graph of this type, okay. So it is changing gradually, not suddenly, not abruptly, okay. So this is how we define the fuzzy set. We will see the by example shortly. So the gradual change in membership value indicates that the boundaries of fuzzy sets are vague and ambiguous. So we can say because there is not a sudden change, there is a gradual change. So therefore the boundaries, they are not properly defined. So it may happen that one element may belong to two different fuzzy sets, okay. Like we consider the example of 30. So 30, that number 30, it may come in a young age, and also maybe in a not or maybe like middle age, okay. That 30 may come in two fuzzy sets. It is possible. But in case of crisp set, one element cannot come in two different crisp sets. Then a fuzzy set is a set containing elements that have varying degrees of membership in the set. So in case of fuzzy set, the membership value, that is mu, it can have any value from 0 to 1, okay, including 0 1. We can have like 0.2, 0.3 up to 1.0 or 1, okay. But in case of crisp set, this membership value, it can be either 0 or 1, not anything between 0 and 1. So members in a classical set cannot be a member in another classical set belonging to the same universe of discourse, because the membership is complete and not vague, okay. So in case of classical set, if one of the element is a member of a particular set, it cannot be in any other set if they are belonging to the same universe of discourse, okay, because here we have membership is complete and it is not vague like in case of fuzzy sets. And members in fuzzy set, they can be a member in another fuzzy set belonging to the same universe of discourse, as membership value may not be complete, okay. So it is vague. Therefore a particular element, it can belong to two fuzzy sets, okay. Now the representation of fuzzy sets. So this is how we represent a fuzzy set. Like suppose if we have a fuzzy set A. Now in this particular tutorial, in this particular lecture, we will denote this fuzzy set by A, and there is a small like this symbol we are using, okay. So this is how we represent a fuzzy set, and this is a classical set, and if we put this symbol here, it becomes a fuzzy set. So maybe if I miss out, it will be there, okay. You can understand that it is there. Now this is how we represent a fuzzy set. So fuzzy set is given by this mu A, where mu A, this one is this is the membership value, and this is called the generic value, okay. So we have various generic values. Now this plus sign is not like we are not doing any addition, but just to separate out the two generic values. So we use this type of representation. Then this is actually a discrete fuzzy set. We can also have a continuous fuzzy set. So this continuous fuzzy set is represented by this particular notation. We are using an integral sign. Actually we are not integrating, but we are just summing up. Okay, we are just using this symbol for continuous fuzzy set. Now in some of the books, fuzzy set is also represented by this particular notation, where this generic value is written, then a comma, and then the membership value is written. Okay, you can just make out the difference. Here we are using this type of representation, and sometimes in some books this type of representation is also used. Okay, now this is the graphical representation. Okay, here you can see there are two graphs. The first one is the crisp set. So in crisp set, maybe this is a particular crisp set representing some quantity. So as we can see, this set is having membership value 1, and outside this membership value is 0. But in case of fuzzy set, if we have a fuzzy set, then this fuzzy set, it may have any value between 0 and 1, including 0 and 1. So this is how we represent a fuzzy set. Okay, then operations on fuzzy set. What operations can we perform? As we saw in case of classical sets, we can perform various operations. So here also we can perform various operations. The first is the union operation. So how we perform this union operation? Suppose in this case, in the graph we were given a fuzzy set A, a fuzzy set B. When we take the union, okay, so this is the fuzzy set A, and this is fuzzy set B. So when we take the union, we take everything which is common to both. Okay, we take everything which is common to both and which is also in that particular set. So this whatever colored is what we have. This is the A union B, and while performing the operation, it is similar to this OR. Okay, so when we are performing the mathematically when we are doing this, so we take the membership value and we take the maximum of the membership value. We will do a problem based on this, then we'll understand. So this is the union operation. Then we have the intersection operation. Okay, intersection operation is given by this particular graphical representation. So in case of intersection, whatever is common between A and B, that is what we get after intersection. This is what we get of the intersection. Okay. And if we do the mathematical calculation, okay, we take the minimum of the two membership values. Then complement. Now here, if this one you can see which is drawn with the orange line, if this is A, okay, graphically, then this one which is drawn with a blue line, that is actually negation of, okay, the complement of A. Okay, this complement of A. Now how do we calculate it? We take the membership value of A 1 minus membership value of A. So this is how we perform the complement operation. We'll see this. We'll perform some operations on the fuzzy sets. Okay, so this operation, that is union, intersection, complement, they are also called as standard fuzzy operations. Then some of the properties of a fuzzy set. The very first is De Morgan's principle. So fuzzy set, it holds good, the De Morgan's principle, it holds good for the fuzzy sets also. So A intersection B is A union A bar, A union A intersection B, the whole bar is A bar union B bar. Then A union B, the whole bar is A bar intersection B bar. Then the law of excluded middle. Now say this is not followed. You can see the law of excluded middle does not holds good in case of fuzzy sets. See, in case of classical set, what we saw, that A union A bar, we get the universal set, but here we are not getting the universal set. You can see why, what the reason is. See this, if we take this one, the orange line, suppose if that represents the fuzzy set A, then it is natural that this line, the green one, it represents the A bar. Okay, so this part, this is suppose A, then this is A bar. When we take the intersection, then this part, you can see this part does not comes in A union A bar. So this part is missing. Okay, so because this part is missing, we cannot say that it is equal to X. If this part is also coming, then we can say that A union A bar is X, that is the universal set. Now see, in case of what happens in case of crisp set. See, in case of crisp set, so if this is A, then everything here is A bar. So if we take A plus A and A union A bar, we get the entire set, but here this part is missing. Okay, so this does not follows. Then some of the algebraic operations on fuzzy set. Okay, so what are the various fuzzy algebraic operations? The first one, if we want to find the algebraic sum, so if we are given two fuzzy sets A and B and their membership value is mu A mu B, then the algebraic sum is given by mu of A plus B is mu of A plus mu of B minus mu A into mu B. Okay, so this is we will see this. Okay, we will solve a problem based on this. Then bounded sum is, if we are given two fuzzy sets A and B, then the bounded sum is given by this symbol. So here we use this particular symbol, okay, and here we are using this plus symbol, and here we have plus and the circle. So this is the bounded sum. So bounded sum, what we do, we take the sum of mu A and mu B and compare it with 1. If it is greater than 1, we take 1. If it is less than 1, we write that particular sum. Okay, we'll see, we will solve one problem based on this. Then we have bounded difference. So if we are given two fuzzy sets A, B, and the membership value is also given, then the bounded difference is given by this particular formula, that is mu of A. Now here the symbol is this one, a dot and a circle over it. Okay, so this is, so we mu A minus mu B and 0. So whatever is maximum of this, it may possible that when we take the difference we get negative value. So we don't take negative values, we will take 0 in that case, and if it is greater than 0, we take that value. Let us see one problem. So we are given two fuzzy sets. These are two fuzzy sets A, B. So A is given in the numerator, we are having the membership value, and 1, 2, 4, 5, they are the generic values. Okay, so let us see the various operations. That is, the first is union, intersection, complement, algebraic sum, bounded sum, difference, and bounded difference. So we start with the union operation. So suppose if we are given this particular fuzzy set, we want to find the union. Okay, so if we take the first case, first one, the first membership value with generic value 1 1. Now out of these two, this 0.2 and 0.4, we see 0.4 is greater, so we write 0.4 for this generic value, and for the second generic value 0.7 is greater, so 0.7 will come, and in the third case 0.3 is greater, so 0.3 is coming here, and 0.9 and 0.6, 0.9 is greater, so we take the larger value. So this is the union operation. Now in case of intersection operation, we take the minimum value of this. Okay, so if we see these two cases, okay, 0.2 is minimum, we write 0.2. For intersection, we take the minimum value, and from 0.5, 0.7, 0.5 is minimum, and 0.3, 0.1, 0.1 is minimum, 0.9, 0.6, 0.6 is minimum. So this is the intersection operation. Then the complement. Okay, so we are given, I am writing this again, this A is given here, this A, I am writing it again, this is the fuzzy set A. Now how to take the complement of this? So we take the first value, so 1 minus 0.2, it is 0.8, so we write 0.8 here. Then 1 minus 0.5, we get 0.5. 1 minus 0.3, we get 0.7. 1 minus 0.9, we get 0.1. So this is the complement. Similarly we do for B. Okay, B also, this is 0.4, 1 minus 0.4 is 0.6, and this is 0.3, 0.9 and 0.4. This is the complement of B. Then the algebraic sum. Okay, now see algebraic sum, this is the formula for getting the algebraic sum, that is, we take the membership value of 2, add them, then subtract with their product. Okay, so I have just performed this operation here. So in the first case, for the first case we have mu A 0.2, mu B 0.4, then minus 0.2 into 0.4. So 0.2 into 0.4 is 0.08, and this is 0.6. So 0.6 minus 0.08 is 0.52. Similarly, this red is for this one. So I have also colored them so that we can distinguish them. So this is for generic value 4, and this green one is for 5. So I have done the calculation, you can check it. Okay, this is how we perform the algebraic sum operation. Then bounded sum. Okay, now what we do in bounded sum, we add the values mu A and mu B. Okay, and if the sum exceeds 1, then we write 1. If it is less than 1, we write that particular value. So let us see, in the first case, for this particular generic value 0.2 plus 0.4, so there is 0.6, which is less than 1, so we write 0.6. Okay, then in the second case 0.5 plus 0.7, which is actually 1.2. As you can see, this 1.2, which is greater than 1, so we write 1 here. In the fourth case, 0.3 plus 0.1, we get 0.4, because which is less than 1, so we write 0.4 here. and in the last case 0.9 plus 0.6 is actually 1.5, which is greater than 1, so we write 1 here. So this is how we do the bounded sum. Okay. Then the difference operation. Okay, difference operation, this is the formula for getting the difference operation. So what we do is mu a minus mu a intersection mu b. Okay, this is the formula for calculating the difference. We have discussed in the previous videos. So this is the operation. So what we do for the first case, 0.2 is mu a minus 0.2 intersection 0.4. So in intersection we take the minimum. So minimum is 0.2. 0.2 minus 0.2 is 0. So we get 0 here, which is what we get 0. Then in the next case 0.5, that is mu a minus mu a intersection mu b. So in intersection we get this as 0.5, and 0.5 minus 0.5 is 0, so we get 0 here. In the third case also we get 0.3 as mu a minus mu a intersection mu b. So out of this we get 0.1, and mu 0.3 minus 0.1 is 0.2, so we get 0.2 here. So similarly also last we get 0.3. So I've just colored it so that these are related. Okay. Then the next operation is bounded difference. Now in case of bounded difference, we take the difference of the two, and if the difference is negative we write 0. If it is not negative, then we write that particular value. So let us see. So first value is 0.2 minus 0.4. So this is actually minus 0.2, which is less than 0, so we write 0. In the second case we have 0.5 minus 0.7, which is minus 0.2, which is less than 0, so we write 0. Okay. And in the third case 0.1, 0.3 minus 0. It is 0.2, which is greater than 0. Which is greater than 0, so we write 0.2. And the last case 0.9 minus 0.6 is 0.3, which is greater than 0, so we write 0.3. So that's all. Now you can just solve this. So this a problem is given to us. I won't solve this problem. So you can see this for a flight simulator data. The determination of certain changes in operating conditions of the aircraft is made on the basis of hard breakpoints in Mach region. So let us define a fuzzy set to represent the condition of near a Mach number is of 0.74. Further define a second fuzzy set to represent the condition on in the region of Mach number 0.74 in a typical simulation data. A Mach number of 0.74 is a hard breakpoint. So don't worry with this whatever the wordings are, it is very very simple. So we are given, you can just consider these two fuzzy sets A and B. Okay, so here we have to perform the union operation. So you can take this fuzzy set, you can take this fuzzy set and the second fuzzy set. Now these are the membership value. These are the membership values. We don't make any changes. These are actually the these are the generic value. Okay, these are the generic values. So we don't need to make any changes in this. Whatever changes will come here. Okay, in the numerator, which is the membership value. So we have to perform union, intersection, a bar, difference, and this one take the union and complement it, and take the intersection and complement it. So we can just solve this as an exercise. Okay, we will continue in the next lecture. Thanks for watching.